This question is taken from the ENGAA 2020 Section 2 paper, and it is question 13. So we read, an elastic cord with spring constant K is fixed to points P and Q on the diameter of a ring. The cord is taut but unstretched. The ring has radius R. The midpoint of the cord is then pulled and fixed to a point on the ring halfway between P and Q. What is the energy stored in the cord? So in order to get the elastic potential energy or strain energy, knowing the spring constant K, we'll either need to know the force or tension in the spring or the extension. So in this case, intuition would lead us to think the extension would be easier to calculate, as we know we're pulling the cord up to the middle of the ring at the top. So if we draw the setup, the purple line will be what the cord looks like now. Then using some simple trigonometry or Pythagoras, we know that the length of each side of this purple cord will be square root of 2r. So this is a very useful trick to know for the actual sciences and engineering admission assessments, that when you have, this would be r and this is r, the hypotenuse is always square root of 2 times the side lengths of an isosceles right angle triangle. So the extension is simply the new length take away the original unstretched length. This is delta x equals 2 square root 2r minus 2r. Again, we like to factorize in these examinations because they make it easier for later on when we know we're going to square this or multiply. So this is 2r factored with square root of 2 minus 1. Therefore, an expression for the elastic potential energy involving half k times the extension squared is half times k times the 2 squared, r squared, and then square root of 2 minus 1 all squared. See again why we factored to make this whole multiplication or squaring a lot easier to deal with. So then we get a half times 4, so it just becomes the 2. And then square root of 2 minus 1, if you square it, you get 2 plus the 1, and then minus 2 root 2. So we get 2 from the 4 over 2, and then this is the 3, which is the square root of 2 squared plus 1 squared, which is 3. And then the third part, well, the square root, so 2 minus 2 root 2 here, and then kr squared. So this is our expression for the elastic potential energy.